go through this. Yeah, welcome to May event of NottsJS, our second remote event, and it's nice that it's number 50. It's a nice round number. So there's not going to be too much intro to this because there's not really much to introduce when we are doing remote events. So I'm just going to go through a few usual things. So hello there, thank you very much for joining. We are persisting on with presenting this, and it's people are very busy, even though everyone's at home or not traveling so much, but people are still busy, so it's still hard to get people to speak. So I do want to ask if you are available to speak. Oop, going through the wrong slides. If you are available to speak, you want to speak. We are looking for speakers. I've had a few people contact us last month, sorry, and we'll be getting in touch with those, see if we can line them up. But yeah, it's a community event, and we'd like a community to contribute. It always helps the community grow if we have the community itself contributing. So we would appreciate that. Also, anyone outside the community, other countries like James here, would be also fine as well. I mean, we've got world reach now. So let me just go back one slide. So this is pretty much solely sponsored by Nearform. James and I both work for Nearform, but that isn't exactly the reason why we're running this. But Nearform are sponsoring the Zoom channel unwillingly. I'm basically just using my Nearform Zoom account for this. But yeah, so Nearform have been with us for a while now, and they will continue to be a sponsor as long as we let them. By the way, if you do need any Nearform, if you don't know, are a digital transformation agency, I guess is the old term, but now the new term is I'm not even sure, the marketing's changed in the company, but yeah, do check us out, nearform.com, and see what we can do for you if you need anything. So I'm not going to go through any more further ado, as I say, and I'm just going to go straight into this. So I'd like to welcome James to the stage. James is a technical steering committee member of Node.js, so this is straight from the horse's mouth, I guess you could say. And he's the research director at Nearform, which kind of nicely plays together. So I'm very pleased to have you with us, James.
Yeah, thank you. Thanks for having me.
So I shall just switch it over if you want to share. Carol's on the stream right now.
Fantastic. Yeah, let me pop this up here. All right, I am sharing now. Oh. Okay, there we go. Still looks like showing you on the video there.
You will get popped over in a second.
Fantastic. Hello, everyone. Thanks for the introduction there, David. I am James Snell. I've been with Nearform for, I think 3 years now. Been involved with the Node project for just over 5 years. Now I am on the technical steering committee, which there's quite a few. I'm not the only one. There's quite a few there. The technical steering committee basically oversees the overall direction of Node. But it's not where all the most of the decisions are made. That's actually just made in the project itself. The technical steering committee basically just kind of helps keep things on the rails, keeps things going, and oversees things like strategic initiatives. These are kind of major changes that are coming into the project over time. Previous ones, things like HTTP2. I'm working on another one right now, which is the implementation of the Quick protocol. One of the strategic initiatives we had there for a while, it's now closed as a strategic initiative, is the introduction of worker threads in Node.js. These were introduced in Node. They were actually introduced in Node 10 as experimental. They graduated in Node 12 as fully supported. And we just released Node 14, and in that time, it's been just over a year. There's still a lot of confusion, a lot of people unsure how worker threads work in Node or how best to use them. We had one issue opened in Node core. I think back in January, and it was kind of a scary issue. This guy was having some memory issues with Node, talking about how he had to run at least 2,000 worker threads at the same time, and he was having some memory concerns and some performance issues. And there actually was a memory leak in Node that was fixed from this. But the key issue here is not what was happening in Node, but the fact that he was trying to run 2,000 worker threads at the same time on a single machine. Most of our laptops or our personal computers here only have about 4 cores, and you have about if you're running about 2,000 threads, they're all kind of contending for that CPU time, and you're going to end up with all kinds of issues. So the immediate problem here is not the memory leak that we had in Node; it was just not using worker threads correctly. But if you go out on the internet and search for it, there's really no documented best practices on how to use workers in Node, and there's all kinds of stuff out there about how to improve performance in Node, but none of them take workers into consideration. Also, if you look at all of the performance profiling tools that are out there, none of them actually understand worker threads, so you can't actually use them to profile the performance of worker threads. A lot of them, for instance, are based on CPU analysis. Well, that's fine as long as you assume that Node is only using a single core for the most part, right? All your JavaScript's running on one thread, and you're only using a single core as you're running that application. When you have multiple threads using multiple cores or contending for the same CPU or whatever else, that picture changes significantly. Other examples are things like memory, heap analysis, whether you're searching for memory leaks and those kind of things. All of the tools that are out there currently are designed to look at just your main Node thread to determine kind of what how you're using the memory and detecting memory leaks and all those kind of things. Every worker thread has its own JavaScript heap. So when you're reporting on those, when you're doing diagnostics on those things, it changes from one to the other. So there's all kinds of things that worker threads change fundamentally about how we reason about Node performance. At the same time, there's a lot that actually doesn't change at all. And if we stop and look at it and think about it, all of the old principles for how making a Node application fast or performant remain the same. But we have to understand how worker threads work in order to really understand how the performance changes, or in many cases stays the same. So what I want to start with first is the anatomy of a Node worker thread. This is quite a bit different than kind of workers in the browser, service workers, anything that people have in mind there. The Node worker thread, it's based on the same API, right? The same basic API. But the underlying internals are actually quite a bit different. Every worker thread has its own event loop. It has its own Node.js environment. So the environment in Node is basically what we consider like the internal state of a Node process, but it also encompasses the standard libraries. So things like the file system module or the net module, right? Every worker thread has its own distinct copy of that entire environment. It also has its own V8 isolate and context. So these are the bits that actually run the JavaScript code and manage memory heap. Anytime you're creating promises or new objects or strings or whatever, right? Every single one of those is managed individually for a worker thread. That said, all of these, the main thread, the worker threads, and everything else, they all share the same libuv thread pool. Now, this is, kind of going back from before, there was this idea that Node was always, single threaded. That's true when we're talking about JavaScript. When we run JavaScript, it was running on a single thread. But in the background, there was always a thread pool provided by libuv that would handle things like file system I/O, or network IO, a number of crypto tasks, that kind of thing. We're always actually offloaded into this thread pool. And then as work would complete, it would kick that back to the main thread and execute. This is something that we'll come back to in a bit, because it's actually fairly critical to the understanding the performance of a worker thread in terms of what kind of stuff is good and what kind of stuff is bad for that worker, right? What kind of workloads, okay? So very important just to understand, it doesn't matter how many worker threads you create, right? They're all sharing the exact same libuv thread pool. And by default, that thread pool on the libuv side has only 4 threads. Now you can tune that, you can increase the number of those, but 4 threads serving, if we go back to the original example of 2,000 worker threads, you're going to run into some performance limitations there. And I'm going to show you some examples that illustrate why. So let's go through some key questions with regards to worker threads. What are the best uses, right? Why would I use them? What kind of workloads are threads best suited for? Are they optimized for IO intensive or compute intensive tasks? These are very, very different types of workloads. How many worker threads can or should I create? And the distinction there between can and should is actually very important, right? You can create many, many, many. You should only create a few. And we'll go through some examples of that. And how do I know if I'm actually using worker threads correctly? Again, there's very little actual documentation out there on this. There are very few resources. So I'm hoping this talk and this video can kind of serve as one starting to get some content out there and get some information going. So let's start going through these. What are the best uses of worker threads? Worker threads are best used to move event loop blocking tasks off the main thread. Right? But only if those cannot be optimized in other ways. So if, for instance, you have a large JSON document, and what you need to do is parse that and go through and process, all of the various elements of that. JSON parsing in Node, when you use JSON parse, is a event loop blocking operation. But it's actually fairly quick. V8's been optimized for this, pretty well, and it does a pretty decent job of doing that. Iterating through those elements, however, especially if you are making changes to that object, can actually be a fairly expensive operation and cause, significant event loop blocking. When I say event loop blocking, it's important to know that, that JavaScript, whenever JavaScript is running in Node, the event loop is not, right? The way that I've described it in previous talks, you got to think of the event loop as a very inefficient letter carrier, mail carrier, right? They have mail for several different people, right? But when they have, they want to deliver a piece of mail to, say, Dave here, right? That letter carrier has to sit there, hand the mail and sit there and wait for Dave to read it, figure out what he's going to do with it, figure out what kind of response he's going to do, and then get a response back to the letter carrier before they can move on to the next person and deliver the next piece of mail. So every time you have a callback, every time you have some bit of JavaScript that's running, that event loop stops and it can't do anything else. What other things can that event loop, is that event loop supposed to be doing? Well, it's checking the IO, see if their files have been read, checking to see if there's new requests that have been received. Anytime JavaScript is running, those other things cannot be happening. So when we talk about event loop blocking tasks, what we're talking about is limiting the length of time JavaScript is running at any one given time. Now, there's ways of optimizing that and reducing that blockage, right? And you don't necessarily want to jump immediately to a worker thread if there are ways that you can minimize the length of time that JavaScript is taking on your main thread. And we'll talk about, we'll show some examples of why that is. But it really comes down to the additional overhead that adding worker threads and using worker threads adds to the mix, right? There's additional things that need to be created. There's context switching. Threads can contend with one another on the CPU, right? There's additional overhead that you have to consider. And sometimes you can get good enough simply by making the JavaScript more efficient on the main thread. So there's, what we're talking about here is just the event loop blocking tasks. Notice that I'm not talking about anything that is asynchronous. If it's already asynchronous, you're not going to see much benefit. And I'm going to show you an example here in a bit that illustrates that. Okay. Next, are worker threads optimized for I/O intensive or compute intensive tasks? Well, this is basically just what I went over. Node is already optimized for asynchronous I/O. It's with a thing that's already been there for from the beginning, right? File reads are asynchronous, network activity is asynchronous. You write some chunk of data to the file system module. That write is actually deferred to libuv thread pool, right? Written out, and then you get a callback when it's done. There is no performance benefit to moving I/O tasks to a worker thread at all. I'm going back to this other example where this guy was creating 2,000 worker threads at the same time. One of the things that each of those worker threads was doing was going out and processing individual files and computing some results on those individual files. Well, every single one of those was actually using asynchronous file I/O. So not only was there creating way too many threads, those threads were actually doing the wrong things that weren't providing any actual performance benefit for the application. You're basically just doing the same amount of work, but adding a bunch of worker threads and promise allocations on top of it that just weren't adding any real benefit. So you got to be very careful in what kinds of workloads you select for a worker thread. Focus only on things that are compute intensive, that are going to take up the CPU time and block the event loop. How many worker threads should I create? No single answer. It's entirely dependent on what the thread is doing, the number of CPU cores available, amount of system memory available, what else is running on the system, right? You might have a 4-core system, but you can safely create, 16, 20, 24 threads that are all working, depending on what those things are doing. The thing you have to watch out for there is that anytime these threads you have more threads than CPU cores, those are going to contend for time on that CPU. So there's going to be some scheduling going back and forth. You're going to see some performance loss as the CPU switches context back and forth. So you have to be very careful what's going on there. If those are memory intensive, that context switching is going to become more expensive over time. So you really have to tune the number of threads that you are creating to the specific types of workloads that you're producing. All right. So there is no single answer. What we have found is that in the code that I'm going to show you in a bit, in kind of a worker pool scenario, you can safely get up to about the square of the number of cores available. So if you have 4 cores, at least 16 worker threads and stuff, you should actually be doing pretty well in a fairly simple Node application. But again, there's no single answer that works that works great. All right. This is the big one. How do I know that I'm using worker threads correctly? And this is the one that is probably the most difficult to characterize. Because again, there is no documentation out there other than the Node core docs that just say how to use it. There hasn't been a lot of performance study out there on these things, or on the impact of it. What we found, though, this issue I mentioned earlier with the 2,000 worker threads is not the first issue we had open in Node Core about people saying, "Hey, I'm having memory issues with my workers because I'm creating way too many or I'm not using them correctly." And in almost every case, it came down to, the old iPhone, you're holding it wrong, right? If you don't know, if there's not a lot of good information about best practices around worker threads, how they work, how to use them, stuff like that, you're going to end up using them in ways that are just not optimal. So to address that concern, myself, Anna Henningsen, Matteo Colina, went off and created this project Piscina, which is a Node worker thread pooling module. You can get it from npm, npm piscina, yarn add piscina, whichever. And what this does is it encapsulates the best practices for creating a worker pool for Node that can go off. You basically you tell it a task, you give it some bit of work that it needs to do, and then you go off and tell it to run an instance of that task, right? So let's say by default, if you have 4 cores, it's going to go out and it can create, I think by default, it creates 1.5 times the number of cores you have in terms of workers. As a max, you submit jobs to it. You get a promise back from that you're going to wait that is resolved when that worker is done performing that activity. It's pretty simple. The API is really straightforward. But what this does is it takes care of the thread creation, thread cleanup, context tracking, the communication, passing those arguments to the thread in a way that performs well. It handles all of the details for you, so you can just focus on the functionality of what your worker is supposed to be doing. In terms of some of the features, we're going to go through some examples of this in a bit. Fast communication between threads, flexible pool sizes, proper async tracking integration, basically some diagnostics stuff built in. Cancellation, so you can go off and schedule some work and you get a promise, but then we have a way of canceling that and canceling the promise. It does support ES6 modules, TypeScript, native add-ons, those kinds of things. So it's pretty feature rich already. This has only been out there for maybe about 1.5 weeks, 2 weeks. So it is pretty new, but it does cover quite a few of the answer quite a few of that question. Am I using these things correctly? By doing most of that for you and making it so you don't have to focus on it too much. All right, so I want to go through some examples. So I'm going to switch over here to my VS Code. So I have a number of a few examples already queued up here, and I want to kind of take some time to explain them first, and then illustrate them. Scrypt is a crypto function built into Node that basically creates a secure hash. It's used primarily for securing passwords when in storage. The idea is that you take some input string and you run it through a hash like 1,000 times or whatever to basically secure it so it can't be guessed. It is designed to be a expensive operation in terms of CPU because you don't want somebody to easily be able to recreate this thing. Within Node, we can generate these synchronously or asynchronously, right? Synchronously it does go off and it blocks the event loop while it generates that secure hash. The asynchronous version, here I'm using a promise-ified version of it. What it does is it actually defers that crypto activity to the libuv worker thread pool. So in JavaScript you say, okay, I want the script to happen, but it actually defers over to libuv workers to handle that, and then returns the results. So when you're using the async version, that's already happening out in a thread pool. Okay. The synchronous version, this is blocking the event loop, right? So what we're doing here, we are for awaiting generating input, but within each one of those async iterations, we're doing a sync, scrypt sync, and a random fill sync. So we're generating some random data, and we're doing the scrypt all synchronously blocking the event loop in that case. So let's take a look at the pooled versions instead. All right. So I have some additional stuff in here for tracking the performance, but instead, in the pooled version, we're going to create an instance of Piscina, which is the thread pool. We're giving it here. This pooled we're doing this asynchronously, so our worker is actually working asynchronously. It's going to do the exact same thing as the unpooled asynchronous version. It's actually going to take that scrypt and defer it to the libuv worker, right? And execute it there and return. And then we have a pooled sync version, which is doing the same thing as the unpooled sync, but just deferring that synchronous scrypt into the worker. Okay. And we can see those here. Now, what you find here is you don't see the sync tasks anywhere in these pooled versions. Those have actually been moved out to separate files, separate JavaScript files here. This scrypt and scrypt sync. This is actually how you define a worker within Pacino. You have a module that exports a function, and that function is what it's called. That can be a synchronous function or an async function. And within that, it's going to complete whatever work you're asking it to do. So here we're saying return await scrypt, giving it the input. We're still doing the random fill, but this version is going off and doing it in the libuv worker pool, whereas this scrypt sync is doing it all synchronous blocking the event loop. Okay, so 4 different variations of the same example. One is unpooled sync, unpooled async, pooled sync, and pooled async. All right, so let's go look at how this ends up working. All right, so I'm going to switch over here. Now I'm using a project called another project that I have called Notare, which let me switch over to it. It's basically a kind of a down and dirty performance monitor for Node. It's fairly new. I published this thing last week. But what it gives you is on the terminal, it can give you information about the memory usage of your process. It gives you a breakdown event loop delay as a histogram. It gives you information about your CPU load and the number of handles, which are how we track asynchronous resources in Node. So it can tell you, for instance, the number of promises that you've created at any given time. Notare has a configurable sampling rate. You specify the number of samples per second it's going to take, and it's going to report it back to this graph tool. We can get into that a whole another time, but I'm going to start it up here at the top. And for this one, what we want to do is take a look at event loop delay. So I'm going to switch over to that. And then I'm going to, let me verify which command lines I'm using here. Okay. Okay, so what I'm going to do is when I start this thing, npm run, I'm going to do unpooled sync. And I'm going to give it a number. 1,000 is kind of the number of input samples it's going to get. So what it's going through is it's going through in that unpooled synchronous. This is the event loop blocking, right? We're going through and generating those scrypts as we go. And if you look up here at the top, you see that the event loop delay, we're seeing a fairly reasonable delay, but I think our sampling rate is not quite high enough. So let's bump that up a little bit. And we're going to do, let's see, we're going to do 49 samples per second. All right, there we go. So we get a little bit more movement, and we can see a little more granularity. What we see here is that we're actually seeing a fairly sizable event loop delay. Unfortunately, on my side here, it's getting cut off by the green on the showing window just a little bit. But if you look over here on the side, you'll see that the maximum delay is actually pretty high over on the side, and we have a drop off where we got about 90% of the tasks are running at a fairly high delay rate. Okay, so let's look at a different one. Let's look at the pooled version or the async version. Okay. All right. So for this one, what you're going to find, what you should see there, if you look over the synchronous delay is much less here. The histogram flattens out. We're seeing far less variance in the event loop blocking here. It's doing the same amount of work. We're still processing 1,000 randomly generated hashes through this thing. But the average event loop delay again, this is not using the thread pool. This is just using the asynchronous version of scrypt that's in Node. The event loop delay is, I think, maybe about 60 times less than what it was in the or 60% less than what it was in the synchronous version. All right, that JavaScript is running faster because it's there's less actually running in JavaScript. There's no event loop blocking that's happening here. Again, this is the unpooled version. All right, so let's look at the pooled versions. All right, so first, let's look at the pooled async. Oh, wrong one. Just pooled. I'm sorry. All right. So what this is doing is it's actually going using Pacina, using the asynchronous version of scrypt and a worker thread. And what you should find is that it looks identical to the unpooled async version. The reason for that is that the node process is doing the identical work that it would be doing in the unpooled async. All of those scrypt operations are being handled by the libuv thread pool, not by Pacina. All you're doing in this case, in the pooled version, is you're creating a worker thread to go schedule work in another worker thread. Right? So it doesn't matter how many node workers we create, we're still bound to the libuv workers and how fast those are able to operate and how much activity those are able to complete. So what ends up happening here is that our node, our main thread and our worker threads just end up waiting the same amount of time as they would when we were doing everything with just on the main thread asynchronously. So in this case, using the Pacina pool in the worker threads gives us zero benefit whatsoever. Okay, but what happens when we use the pooled sync version? Yeah, and we run this. What we'll find is that if you remember the sync version of this, the event loop block was really high. In this case, the pooled sync version looks almost identical to the async unpooled and the async pooled version. Again, it's because it's doing the identical work, right? All we're doing is doing that scrypt operation in another thread off the main event loop, right? So it's in this case, moving that synchronous activity to the worker threads was identical to performance was identical to using the asynchronous version of scrypt that's already built into Node. The point of all this is that if you are using Node APIs that already have an async option, right, you are not going to see any benefit to using a worker thread, right? This includes things like file system reads, network activity, going off and querying a database, anything that is I/O bound or bound to an async operation. None of those things are going to benefit from using a worker thread. Where worker threads benefit the most is if you have an event loop blocking operation, a synchronous operation, right, that cannot already be deferred to the libuv thread pool, right? So the example of that would be this pooled sync. If we did not have an async version of scrypt, for instance, right, we could move that into a worker thread and achieve the performance benefit of having the asynchronous version. Okay, hopefully that makes sense. All right, so let's go into look at another example. All right, so this other example that we have creates a server. It's very similar to the scrypt one that we just had, but we have four versions. Again, pooled, synchronous, unpooled, synchronous, pooled async, and unpooled async. Right. So we have a couple different versions here. Now, what these things are doing, it's just very, very, very simple. And we have we're basically using a synchronous sleep and an asynchronous sleep. The synchronous sleep uses atomic weight to force the thread to block for up to 100 milliseconds. The async sleep uses a promiseified version of set timeout. Let me see here. I'll find it. A promiseified version of set timeout, the sleep. And what that does is it uses a timer to allow the event loop to spin while that is sleeping. Okay. It's almost the same example is the S script here. Just, we're wrapping it up into a server and showing, that it is possible to use these things on the server side. But I want to show the impact in terms of requests per second and the throughput on these things. All right, so on event loop delay, let's see. Yeah, let's keep it on event loop delay here. We're going to switch over to the server example. Okay, so the first thing we're going to do is we're going to run npm run. We're going to use unpooled sync. Nope, I think it's sync unpooled. Okay, just pooled. I had them flipped. All right. So we're going to use unpooled is the asynchronous version of this sleep. So this is using the using atomic weights. So we're going to use autocannon, which is another which is an HP benchmarking tool. Now, if you look at the top here, what it's doing once I've started this, Natari is basically giving us the baseline event loop delay as the histogram. So right now, the thread is doing, the node process is doing nothing but waiting for a request. Okay, so we're going to throw about a 10-second benchmark at this thing. Oh, and we see the event loop drop off. The delay skyrocket pretty much immediately. And we're not doing a. Let me increase the sampling right here. Sorry, HC49, so we can see that a little clearer. What you'll see here is that even though I increase the sampling rate, because we are blocking the event loop, we're actually blocking the sampler from being able to run efficiently as well. But we are still getting these really high event loop blocking rates over here at the top end. Okay. Again, just because we're sleeping synchronously, and if you look here, requests per second at 50%, we're only getting about 10 requests per second, with an average of 9.6 requests per second. Not very good, right? So we're blocking that event loop. It's not able to do much of anything else. All right. So let's look at the unpooled async version. Okay. Again, we're going to let the event loop delay kind of normalize out there for a second. And then start applying our load. What you'll see on this is that as it starts reporting, it's actually not reporting much of a change in the event loop delay at all. All right. And it's because we are sleeping asynchronously. We're allowing the event loop to turn. We're not blocking it for every single one of these requests. So that histogram for the event loop delay doesn't actually change much. We've got our requests per second go up to 100 at the 50% mark here, an average of 98. Okay, so using that asynchronous, by deferring that asynchronous activity, right, and moving it off the main thread, we're actually seeing a tenfold increase in the request per second performance of this thing, right? We're sleeping those requests the same amount of time, but we're able to process more as we go. And again, this is not using Pachina. All right, so let's go through and use the Pachina version. Let's go pooled. Let's see what it is. It's async pooled. Okay. We're going to let that normalize out and throw some load on it. We're going to see quite a bit more variance as we go through the event loop delay here as it goes through the examples. But you'll see that the event loop delay is actually about the same as the as the asynchronous version was. But look what happens to our request per second. Using Pachina actually caused our request per second to drop down to 60. That's because it's still doing that async wait, right? It's still using the promise-fied set timeout to wait. But we using the worker threads, we've actually introduced additional overhead that we didn't have in the other version, right? So you have the additional workers, you have additional promises that are being created, you have additional work that process is having to do, and because of that, right, it's still doing the same amount of work plus all these additional allocations. It actually kills your throughput. So again, some benefits to using workers, right? And some cases not. But let's look what happens when we have the synchronous pooled version. Okay. Okay, so this is we're using that atomic weight to block the event loop, right? To block the execution, but we're deferring that to the worker thread. And let's run that load. So in the first case, using that sync sleep gave us 10 requests per second, right? It was pretty bad. In this case, right, when we have that, we're actually getting it up to 60 requests per second. So again, which was identical to when we had the async sleep in the worker thread. So in this case, again, just reiterating and proving the point, the only performance benefit that you're going to get when you're using worker threads is if you are moving your synchronous event loop blocking operations off the main thread into the worker. They add no benefit whatsoever if you are deferring a task that is already asynchronous. All right. In fact, you could actually kill your performance by doing that, by moving those async IO operations off the main thread. Okay. All right, one more example to go through, and then we can wrap it up and open up for some questions. So the next example that I have, Pacina is a queue, right? It creates a pool of workers, worker threads, queues up tasks. But how many tasks should you queue up into this thing? Pacina actually, has some mechanisms where you can limit that, and you have to kind of ask like, okay, well, why would I want to limit what's in my queue? The reason has to do not necessarily with how fast this stuff is running, but how efficiently it's running, and most specifically, your memory usage of your node process. The more you queue up tasks, and the more workers you create, the more heap space, the more memory your process is going to be using all at the same time. And what you can see are inefficiencies caused by garbage collection runs or using way too much memory for your process, right? One, it can cause your AWS hosting bill to skyrocket, right? If you're using just too much. So what we did with Pacina is actually made it possible to tune not only the number of workers that you can create, but the number of tasks that you can queue up at any given time. And what this example does is it actually creates a stream that goes through and parses a CSV, a common separated value list that has about 25,000 entries in it. It goes through and processes those one at a time, and then kicks off a worker thread task for each one of those lines, right? So we're creating up 25,000 plus jobs that these workers are processing. And the way this example is set up is I can tune it tune the actual batch size. So I can tell it, hey, process all these at once, or 20 at a time. And what we're going to do is take a look at what the impact of that has in terms of runtime, in terms of memory use, and a few other dimensions. Okay, so with this one, I actually want to switch over to where it's looking at memory. I'm not going to use that one anymore. Let's see. Let me switch over to streaming. Let me just verify. Okay. So npm start. Okay. So again, what this is going to end up doing is when I start this, it's going to open the CSV, start streaming through and processing those entries one at a time, right? And let's say I put in, let's go 5. Now I got to increase the sampling rate here so we can see this. So I'm going to process about 500 of these at a time. What we see here on Pacina, it's got, fairly, memory's not too bad, right? Let's kick this up to 5,000 of these at a time. And what we see over here is that the memory, the heap usage, which is, we got the heap total, which, the red line up the top is your total RSS. That's the total memory for your process. This middle line is your total heap that V8's allocating. And then the bottom line here is your the actual heap used in this case. And again, and this is sampling 49 times per second. So as we increase the number of the batch size of the max queue, the number of things that we can queue up into this Piscina queue, we see that the memory pressure starts to increase fairly significantly. Let's go 10,000 of these, right? And that memory increase becomes much more dramatic. Okay, let's look at what's happening here. In the output, we have some, there's a number down here that gives us the run times. So when we had 10,000 items, our runtime was about 943 milliseconds, which is here. When we batched, when we batched 500 of them, when we batched 10,000 of them, it was about 939. Not a huge variance, but a fairly massive, sizable variance in the memory that's actually being consumed. Right, so we're trading off, the performance, the runtime, the actual wall time for these things getting queued up is about the same. It doesn't change much, but the amount of memory we're using varies significantly. What happens if we drop this though? Let's just say 16, right? So our max queue is only 16 items at a time. What you find is that our wall time for actually running this code increases a little bit, but not significantly. But our memory usage flattens out. And the reason for this is we are, at any one time in the process, we are only processing a small number of items at one time. We're only allocating a small number of objects at any one time. So it does extend our execution time out just a little bit, right? But it makes our memory consumption much more predictable and much more manageable. Okay. Now I want to put one additional dimension in this. Notori, by default, we have one of the screens at the end is handles, and what this is doing is it's tracking the number of asynchronous resources that Node is keeping track of at any one time. By default, that's turned off because it's a fairly expensive operation. Just turning this on gives you a 30% performance decrease in your Node because it's using async hooks, the API built in. It's a fairly expensive operation. So we have it off by default. So we're going to turn it on. And we're going to use Notori handles equals 1 to switch that on. And I want to show specifically, this is going to show a number of different objects, but I want you to pay specific attention to the promises column and what happens to that. So when I run 16, that varied quite a bit, but here at the end, we'll just look at the end. What this is showing us is the number of promise objects that were being tracked, by the async hooks API at that sampling rate. So here, this is telling us that when it took this last sample, it was just over 1,200, just under 1,300 promise instances that were in memory at that time. Okay. Those are things that were still waiting to be garbage collected. And that variances, when we have 16, it goes by quick, but if we run this, it spikes up to, I think, about 2,400 promises at any given time. While our sampling size, our queue limit is at only 16. What happens if we increase this to 10,000? Again, this is 10,000 items in the queue at any given time. The way Piscina works is it creates a promise for every single one of those tasks. So where are we going to spike at? Here, at this particular sample, it goes up to 19,800 promises. And if you watch closely while that was running, that actually spikes up to over 24,000 while it's running at one particular sample time. The point is we're increasing that batch size, yes, but we're significantly increasing the garbage collection pressure and the memory pressure by allocating an order of magnitude more promise objects as this thing is running. So it's not always about wall time on execution. Sometimes it's about how much memory you're using or not using, or keeping that leveled out as we go. All right. So those are the three examples that I wanted to show. Just goes back to the the point on promises themselves. One, only use the promises that on the worker threads. Only use a worker thread to offload synchronous event loop blocking tasks. That's the only time you're going to see a noticeable, measurable performance benefit. Limit the number of worker threads that you're creating. Your system might allow you to create thousands of these. You're only going to need a handful. Generally, keep it within a certain multiple, a modest multiple of the number of cores you have available, depending on what else you have going on that system, right? And keep in mind that you're always, especially whenever you're doing anything that's IO related, you're always going to be limited by the libuv thread pool, which is tunable. You can actually increase the number of threads running in that pool. But the more you increase that, both thread pools, the number of workers that you're creating with Pachina or anything else, and increasing the size of the libuv thread pool, all you're going to do is create more CPU contention. So you can end up shooting yourself in the foot, thinking that you're making increasing your capacity, but if you're still limited on the number of cores you have, you're not actually going to give yourself any benefit. So that's the when it comes down to it, that's Pachina. It is an open source project. Happy to have folks come take a look at it, contribute it. It is work that's been sponsored by Nearform Research. It's out and available. It's only been there, I think, for like maybe 2 weeks. So it is brand new. Kick tires on it. Let me know what you think. The whole reason Pachina exists is to give an answer to the question, how do I use worker threads correctly? Right. The answer is you want to use a tool like Pachina that does most of the work for you. So that is it, and I can open it up for questions.
Thank you, James.
I know Dave, you had a few.
Yeah, that was intense. lots of things to pay attention to there. We have a question here from Wujay. I don't know if you can see the Twitch chat, but I'll read it out.
Yeah. Yep, I got it.
Are there any notable libraries / frameworks which are taking advantage of workers at the moment?
There are a few. Cindersaurus has a few. There's one in particular called Hasha, which goes through and does it generates hashes for files using the workers. But as I pointed out, it's going off and doing the file IO and the workers. So it's using them, but whether or not it's using it effectively is a whole other question. There's not a lot out there that are using them, but I would say correctly. But we are starting to see examples of them.
Have you benchmarked that particular project to see if it's to see how useful worker threads were?
Yeah. So that's one that that I was actually testing last week there, and there's really no performance benefit being gained out of the way that they're using it.
Okay, that's a shame, but at least they're using them.
Yeah.
Wujay is John, and he's thanking you for the answer there. I have a question actually. So you mentioned AWS at one point.
Yep.
And I was thinking throughout this, should I use this with AWS Lambdas? Should I use worker threads?
So that depends. Again, all the same rules apply. If what you are offloading is a synchronous blocking task, then absolutely. But a lot of folks are using Lambdas to basically, proxy to other services. So if you're using a Lambda to go off and, talk to, S3 or to route requests to a database, right? You're not going to see a significant benefit out of it because those types of operations are bound to your libuv thread pool and the IO operations, right? It's already bound to your async IO that is already there in Node. You're not going to do any better than those unless you are taking whatever synchronous block of logic that Lambda is doing, and moving it out to the workload. One example of this is, so if you're creating a pipeline, so it kind of goes back to that example with the stream in, right? If you were creating a data processing pipeline, okay, where some steps are async, but some steps are synchronous.
Yep.
You can actually set it up so that in that pipeline, your synchronous step is actually being done in a worker, but everything else is being async on your main thread, right?
Yeah. So subdividing the work that you need to do overall.
Right,
Yeah.
right. So that kind of model works great, but then any actual I/O that you need to do, like updating the database, whatever, you would just return back to your main thread and do it there. That's that main thread is where you should always be doing any of your asynchronous I/O. Okay. So dividing that up a little bit. Now there is another project that we're working on that we Anna, myself and Michelle, that we're working on that actually wraps a message port. A message port is the API you use to communicate between worker threads. The main thread and worker thread is used to pass data back and forth.
Yeah.
We're creating a module that allows you to wrap that in a stream duplex. So you'll actually be able to communicate with these worker threads using the normal Streams API. So if you have these kind of tasks where you just want to offload some synchronous processing to a worker, it should be pretty straightforward.
Actually, now that you mention it, I was going to ask about is the message port still? I can't remember the name for it, but it can only transfer objects and primitive types, right?
Yeah. So there's when you're the message port, it can clone or it can transfer. So if you pass it a regular object, any JavaScript object, by default, what it's going to do is create a copy. V8 has a serialization and deserialization protocol built into it that will, basically efficiently copy that over to the worker. It works for most object types. If you have something like a typed array, a uint8 array, int16 array, a buffer, right? You can actually transfer, use a transfer list instead. What that does, instead of copying it, right, it just moves the ownership. So we finally, someone was celebrating about this last week sarcastically. We finally have move semantics in Node and in JavaScript, and it actually causes some problems. You have to, in order to use the transfer list, it has to be a shared array buffer, right? Or it can be a regular array buffer, but you have to make sure you own it. And this is a bit subtle, but within Node, when you create a buffer instance, right? So buffer.from and give it some data. That buffer is a uint8 array, but the underlying array buffer actually is a pre-allocated pool that all other buffers in Node share. Right, so all you're doing is basically slicing off bits of pre-allocated memory. When you send a buffer or any typed array, when you transfer it, it's not that typed array that gets transferred. It's the underlying array buffer that gets transferred. So if you attempt to, transfer the pre-allocated buffer, it used to be that Node would crash. Now Node forces it so that always gets copied. So you might think you're only transferring a 10 byte buffer, but you're actually copying an 8K pre-allocated a bit of memory. Yeah. And all of the contents of those buffers that you did not intend to transfer get copied over. And then if you transfer other buffers that are not allocated off that pool, there may be other bits of native code in Node that are still using those, so you can end up with things like seg faults and hard crashes because you've suddenly invalidated the memory addresses that you're transferring. We're still finding all of those. We just found it, I think, 2 of them last week, where this happens. So you have to be very, very careful using a transfer list and make sure that you are only transferring the things are safe to transfer.
I guess most
So
people will be using objects and strings and
yes,
numbers.
yeah, cloning, cloning
Yeah,
those is safe.
but I guess that is some degree of overhead anyway in using
Yeah,
worker threads. I mean, I've
yeah,
seen the same thing on browsers using workers on there. You pay the penalty of transferring the object, and sometimes it's
yep.
better just to leave on the main thread.
Yeah, yeah, absolutely. Be very selective about what you're transferring and what you're copying. I mean, if you're taking yeah, I have one customer I was working with. Their JSON files were like at least a meg in size or larger. They were parsing these things and trying to do some stuff. And one of the questions I had was, "Well, would worker threads help us process these?" I'm like, no, it's a massive amount of data that you're working with. The way that you're doing it, it's not going to give you any benefits.
I guess one of the things you could do with worker threads is actually instruct the worker thread to get its own data rather than transfer
Yeah,
it.
you could, but again, that goes back into the I/O issue.
Mm.
So what you have to do is balance out, yeah, profile it both ways, right? Do the I/O on the main thread, transfer that, or you could stick all that into a shared array buffer, right? So and just transfer that shared array buffer over.
Yep.
So you have to profile. There's no single right answer, other than test, benchmark, and see what works best for the workload that you're creating.
Which is a good reason that NotesJS exists. So now
Oh
you've
yeah,
got something to do this with.
yep, absolutely.
So actually, one final question from me is: what do you think is the most common use case for worker threads now using Piscina?
Um, Hard to say. Except Pacino only existed for like 2 weeks. So it still needs to be kind of put through its paces. Um, what I would imagine, what I'd probably recommend. We have a lot of folks that like to do, like I said, with JSON documents. They'll parse these large JSON documents, and then go through and do a iteration over all of their fields, right?
Mm.
Um, and see if those things need to be updated or whatever else. And it tends to, absolutely kill your event loop in terms of blocking it way too long. Those kind of tasks would be good for a worker. Again, you have to figure out how you're going to get the data into the worker, but actually going through and doing that processing. Another thing that I'm looking to explore, I haven't quite got into it yet. There's two things. One is the server-side rendering. We're actually doing some experimentation with React server-side rendering, moving the actual rendering process itself into the worker. That tends to be a fairly expensive operation in terms of blocking the event loop, and historically has always been a source of performance issues. So we're going to experiment with that a little bit. Specifically doing some tests, or kind of a modified version of Next.js that I'm working on to try to see if I can get it working with this. Still far from having that be a usable result. The other one is GraphQL processing. So GraphQL, when you receive a query, it has to be parsed, turned into AST, walked, and then have an execution plan put together for it to figure out, how are you going to actually execute this before you actually get to the I/O of actually processing it. We've done some research in the past. We at Mateo and Mateo's Boost, as part of Nearform Research, they went through and did some exploration on how they can improve performance of GraphQL in general, and they achieved some very significant improvements through compiling and pre-compiling hot queries and caching, things like that. I want to see if we can get some additional benefit out of offloading some of that work to workers, and where we're still processing the main I/O portions in the main thread, but all of the synchronous blocking tasks are happening off thread in the in workers. And so that's something that probably in the next few weeks I'll start kind of experimenting with.
Good. Well, thank you very much. I don't have any more questions. Well, I do, but we could go on for for a long time, so I'm keeping them to concise questions. Um,
Fantastic.
but these are fantastic tools that you've shown today. So Piscina and Notaire, and I would like to actually tweet out those links to those projects.
Yeah,
Um,
absolutely.
are you looking
I
for?
I'll drop them into the chat here as well. I mean, they're both on npm and both on GitHub. So
Great. Ah, nice one. Okay, so yeah, thank you very much. I guess there's nothing else for me to say either, other than thank you very much, James, and I will clap. Hopefully everyone else is clapping as well.
Well, I definitely hope that, I definitely hope it's useful information and folks got out of it. If anybody does have any questions at any time, hit me up on Twitter. I'm James Snell there. Same thing on GitHub. I'm easy to find. So
great. I'm trying to look at what the next date our next event is, but I should know this. I think it's 9th of June. So I don't know what's happening yet, but 9th of June we'll stream again, and I will archive this particular video. Maybe even put it on YouTube. I haven't worked out all the rules and regulations for this yet, but we'll see.
fantastic. Yeah, I think we're all getting used to this. All online digital content creation.
Yeah, I'm not a content creator. I'm a content consumer, so this is new for me.
We're all going to be experts in OBS by the time this is all done. Like we'll always be able to get jobs in broadcasting after this, I think.
You should see the setup I've got, like Mac and yeah. Oh, I'm using Wi-Fi, so I think it went a bit jittery. I forgot to plug in my my actual gigabit network cable. So whoops. Okay.
Alrighty.
Thank you very much, and we'll close the stream here. So yeah, keep posting questions, and I'll probably forward them to you if we get any more after the stream's ended.
Absolutely. Sounds good. And thanks all for watching.
Yep, thank you to all the viewers, and thank you everyone else for helping out. Thanks, Carol. And we'll see you next time. Bye.